Welcome back to topic 2, exponential logarithmic functions. Today we are looking at transforming exponential functions. And we did this a little bit in our previous topic of function transformations itself when that was introduced, and we talked about the certain parent functions. We are going to look a little more closely at exponential functions in this unit, of course. And we'll start this particular part by just straight up trying to graph some things. Now, looking at the function itself, where we say that y is equal to f of x, and that we have 4 parameters for transformations, what could they possibly do? We recall that a is a vertical stretch factor, so we'll be multiplying our y values by a, our y values, because it is a vertical effect. And the other vertical effect is k. We've got our vertical translation, so we're going to add that to y. B and h are horizontal effects. They happen inside the function brackets here. B being a horizontal compression factor, so we divide x by b. And h is number of units of horizontal translation, so we're adding h to x. And what does that look like in exponent form? If we're saying that f of x is equal to some value to the power of x, anything we put in for x goes in here. So if we're talking about f of bx minus h, then we're talking about c to the power of bx minus h. So anything we see in this exponent, we can essentially go with as saying is a horizontal effect. And anything outside, maybe a coefficient here or something added there, that is a vertical effect. Because the function says take your input and put it in this exponent. So that's what we'll be dealing with, and it'll be pretty great. Honestly, feel free to just give these a go right away and see what happens, because I'm going to dive right in myself. This will rely on your ability to graph the parent exponential function and to transform things as well. I don't know if I ever mentioned this, but I tend to put my scale last of all things, but always make sure you label your scale on your axes. As I do this one, I'll tackle it through transformations. I will do a dotted line for the first one, which is 2 to the x, which has a point at 0, 1 and 1, 2. I can get some other points in there as well, if I so desire. And remembering that this is not my final graph, this should be a dotted line. If it's solid, then it's being treated as my final answer, which this is not. What are we doing in this graph? Is this horizontal? Is it vertical? We know it is vertical because for exponential functions, it is not in the exponent. It's out here. So that means we have a vertical stretch factor of 3, and we will multiply all these y values by 3. In we go. 1 times 3 is 3. 2 times 3 is 6. 4 times 3 doesn't even fit on the graph. We could probably get a few others, like 1/2 times 3 is 1.5. 1/4 times 3 is like 3/4. So we can get decently in there. But generally looking at the same shape. And now I'll use the solid curve because this is, of course, the final graph. That one is done. Again, try it yourself. Ooh, again, I should put my scale in here, where that's a 1. We'll say that's 4. Worth noting, like you don't have to label it 1 and 1. I prefer to label my scale last so I can put it at places that don't really interfere with what I'm writing. I wouldn't want to write like a 2 here because that'd conflict with the space here. But anyhow, continue to try these other ones. Again, I'm jumping right in here. I'll start with this parent function. is still 2 to the x. So hooray, huzzah. I've got my dotted lines. Super duper. Doing a couple things to this. Looks like we're going, what direction is that? To the right. Going right 3, and we're also going down 2. And that's exactly what I'm going to do. I'm going to take all my points. I'm going to go right 3 and down 2. I'm going to go right 3 and down 2. And do that for all of these things. And as that's changing, we note that our original graph had a y asymptote, or sorry, horizontal asymptote. And that was at y equals 0. In transforming that, moving it to any horizontal effects don't affect y, so we don't have to worry about that. But this down 2, we'll say that that y value gets subtracted by 2. So there it is. Y equals -2 is the new asymptote. We do need to make sure we draw that. The asymptote is a dotted line. It is not actually the graph itself. It just kind of helps indicate what's happening with the graph. We do need to label it. And now we can play our connect the dots. Again, always going for a nice smooth curve. There's no sudden jarring changes. There's no pointy spots on this function. So draw it like you care about it. Oops, scale. That can be 1. That can be 3. We're still dealing with 2 to the x as the parent function in this case. So we still have those same original points. We're still using dotted line for that. And a couple things happening here. Looks like we have a vertical flip. And we have to go up by 3. And that means our new asymptote will be at y equals 3. And we'll get that eventually, but let's do the flip first. In, sure, darkish blue. So doing a vertical reflection, which we should be comfortable with at this point, gives us that. And then shifting this whole thing up 3. I might start by drawing my asymptote, to be honest. And then the graph itself. So all points up by 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. This is me connecting the dots. La la la, la 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 la. And of course, this time I'm remembering to do my scale before I move on to the next example. What a star. And this last one, it's not 2 to the x as our parent function. We're dealing with 3 to the x. We'll still have 0, 1. We've established that is a common point to all the parent functions. There go my keys. And this one will have the 0.13. Next point, if we really wanted it, would be at like 2.9. If we wanted it. But who knows? And we can still use it. There's no harm in that. Be aware of it. Because we're going to do a bunch of things. Oh, you're right, I did switch colors. Didn't want to. Sorry, everyone. Sorry. 2, 3, and 9. Okay. I do recognize that it doesn't look like I care as much about the dotted line version I'm drawing. That's because the dotted line version is just giving me an idea as to what to do. It's not actually showing what the graph is. You're just setting some things in motion. We do have a few things going on. Of course, that's we're going to squish by factor 2. We are going to horizontally reflect. And then this thing says down 5. I might take this in 3. So looking at the vertical squish factor of 2, everything gets cut in half, which is not the prettiest for powers of 3, but there we have it. We are reflecting horizontally, so over the y-axis. That stays there, that's there, that's there. Still dotted lines, still not done this thing. And then down 5, which means I'll have my asymptote. Over there. And let's finish this thing off. 1, 2, 3, 4, 5. It's there. 1, 2, 3, 4, 5. What's half of 27 minus 5? It's like, oh, it's like 8.5. Oh, it's just above here. Oops, I mean just above here. Nailed it. All right, let's rock this party. This is now our actual function. So we'll do our nice, pretty curve. Always so nice. That. You can't see me physically doing this, but I am rotating this device as I draw this curve. So you have the ability and freedom, in fact, to rotate your own paper as you're drawing that curve, just to give your hand a nice angle to do it at. That's that. So that's how we can graph exponential functions. You don't absolutely need to go through all the stages of transformations if you don't want to. If you wanted to see where key points are mapped to, then all the more to you. If you don't need any dotted lines, go for it. Follow your heart. However you can do this most efficiently would be super duper. Now, some things worth noting are that we employed all the parameters, A, B, H, and K. The thing is, by the nature of the exponent laws, it's actually possible to write everything in this form. So we're going to give that a go. For example, we have a couple of horizontal parameters here. Oh, just the one horizontal parameter. And we don't actually need to pretend that there's a horizontal parameter at all. we could say that in this case, we have 2 times 5 to the power of negative 1 times x plus 3. But that's the same as 2 times 5 to the negative 1 to the power of x plus 3. And we could say that's the same as 2 times 1 over 5 to the power of x plus 3. These two things are the same. And I did that because by this one, for this rule here, the fact that if you have a to the mn, it's the same as a to the m to the power of n. So if you have a power of a power, you just multiply the exponents. That's the rule I'm using here. And we can do that for all of these. So just finding a way to break up the exponents. How do we break up this kind of exponent? I don't know. Give it a try. See if you remember exponent laws and see what happens. And I'll do it right over here. If I delay this out again, I would probably put this stuff over there. Not too bad. If we have a sum in the exponent, well, that's using the rule that if you have a product of powers, you add the exponents. So that's what I'll use here. That's 1/2 to the x times 1/2 to the 5. Again, by this rule here. I'm just going to erase that. I'm just going to move that there, as well as the other one. Then we can start evaluating things. We have 8 times 1/2 to the x. 1/2 to the power of 5 is 1 over 32, and minus 1 from there. Order of operations is still being preserved here. There's a whole bunch of multiplications, and then the subtraction after. We are not subtracting this 1 from any of these things individually right now. We're not turning this 8 into a 7 because of this minus 1. No. Order of operations gets preserved. So we could say we have 8 over 32 times 1/2 to the x minus 1. And finally, that's got to be simplified. Make sure you simplify all your fractions and radicals and stuff too, but keep your answer fully simplified. Otherwise, that's bad for your communication errors. That's done. Wow. And that's done. Final example on this page, before we look at getting the equation from graphs, is this one. Same general ideas. We've got 1/10. How do we want to do this? Oh yeah. We've got 2 to the negative 1 to the power of x minus 3. So that's 1/2 to the x minus 3, which means we've got 1/2 to the x times 1/2 to the negative 3. And evaluating that 1/2 to the negative 3, we get 8. So really what we're dealing with is that. And don't forget to simplify those fractions. So we look at this original function, which had a bunch of things going on. It had a vertical stretch factor of 1/10. It had a horizontal reflection. It had a horizontal shift. Had a lot of stuff, but really by using exponent laws, we changed it into something that only has one transformation going on. And that's kind of nice. And because we can phrase all of our exponential functions in that form, it makes it a lot easier to actually determine their equation. We can first get the value of k by getting the asymptote. So whatever the horizontal asymptote is, that's your k value. Straight up, boom. By mapping, we can find another value because the graph will always contain the point 0, a plus k. So when x is 0, y is a plus k. At that point, we already know k, so we just take that y-intercept and say it's equal, and if we subtract k from it, we get a. But of course, there's a third thing, and that's to figure out which parent function is being used, and we need to know how to find c. For that, we can use any other point on the graph. What color do I want to use for this? So whatever that point is, we'll put the x value in for x, we'll put the y value in for y, and we'll solve. But any other distinct point we can find, that's what we'll be after. So we've got 2 examples of that. Let's go. Honestly, give it a try, see what happens, because it's okay to make mistakes, just as long as you correct them after. So it gives us a try. I'm going to go ahead right now. You feel free to pause, do whatever you need to do. I'm going to start by saying that the asymptote is at y equals -2. Therefore, k is -2. We have a downward shift of 2 because that's how the asymptote changed. Next up, the y-intercept is at -1. Therefore, a plus k is -1. K is -2. So isolating a, boom. And then to get the c value, I need some other point on here. And there are a couple of options. I see a point right here, and I see a point right here. I don't want to reuse this. I just used it to get one of my other values. It's not going to help me to get anything else, because really that point's going to be common for all parent functions. So I have to use one of those 2. And personally, I prefer to work with 1s, so I'll use that point. So from the point, which is -1, 1, we can say that since y is equal to a times c to the x plus k, well, y is 1, a is 1, c is what we don't know, x is -1, k is -2, and we solve for c. 3 is c to the -1, therefore c is 1/3. And putting everything together, y is, okay, so a is 1, we can ignore that, c is 1/3 to the power of x, and -2. This thing's done. Over here, another one. Again, pause if you need to, but here I go. Y is 1, therefore, we have shifted up by 1. The y-intercept is at 5, therefore, a plus k equals 5. Neat. And then finally, we need some other point. I see one here. So using the point 1, 7, we can say that since y is equal to ac to the x plus k, that 7 must be 4 times c to the 1 plus k. Oop, I know what k is. What am I doing with my life? Oh, k is 1. And then we need to solve for c. So 6 is 4c. C is 6 over 4, which is 3 over 2. Always make sure you simplify. And putting it all together, a is 4. Our parent base here is 3/2 to the power of x plus k, which is 1. And then this one is considered done. If you have any questions or comments or concerns, please do make sure that you bring them up to me or find some resource to help you with that. But don't let any unresolved issues remain so. So make sure you get those addressed. Contact me via Teams if you so desire. Or if you are able to see me in class, then see me in class. There is some practice work from the textbook that I would very strongly recommend doing. Make sure you are secure with those, because we will be using this stuff as we go forward. That's all I have to say today. I hope you have a lovely life.